The atomic nucleus is a dynamic object. If struck with a specific particle, it splinters or fuses, releasing a large amount of energy. This is a nuclear reaction. It is a physical event where a heavy nucleus breaks apart or light nuclei combine, transmuting one element into another. Effectively tracking these changes requires identifying how specific particles are reallocated across the reaction. To track this, we use two variables. The top number, A, is atomic mass, representing total nucleons. The bottom number, Z, is atomic number, representing total protons. The fundamental law is conservation. Whatever mass and charge you start with must perfectly equal the final sum. Understanding how to balance these particle equations is necessary to grasp how we engineer nuclear power or attempt to replicate the conditions for fusion. Balancing this microscopic ledger allows physicists to determine exactly which reactions are physically possible. These reactions are categorized by their shorthand notation, the incoming particle followed by the particle that is emitted. In a p-alpha reaction, a proton strikes a lithium atom, forming an unstable intermediate state before dividing into two distinct alpha particles. The math confirms conservation. 1 plus 7 equals 8 input mass. The two alpha particles each equal 4, perfectly balancing the output. A second pathway is the p-n reaction, initiated when a proton strikes boron. The nucleus stabilizes by ejecting a neutron, leaving behind a carbon-11 nucleus. In a p-gamma reaction, a proton hits carbon-12, creating an unstable nitrogen-13 nucleus. Nitrogen-13 achieves stability by emitting a gamma photon. This releases energy without changing the atomic mass or the atomic number of the nucleus. This process can also be reversed. By striking a nucleus with a high-energy gamma photon, the impact can break it apart, a process called photodisintegration. These blueprints prove that in the atomic realm, mass and energy are reconfigured, never lost. Nuclear fission is the practical application of these rules, involving the fracturing of a heavy nucleus to extract heat. The primary method bombards uranium-235 with a single, slow neutron. It is absorbed, creating uranium-236, which is highly unstable. The isotope fractures, splitting into lighter barium-144 and krypton-89. This split releases a large pulse of energy, labeled Q, alongside 3 free neutrons. The conservation holds. The 236 mass units from the input are accounted for in the barium, the krypton, and the 3 neutrons on the output side. These 3 neutrons provide the mechanical trigger for a chain reaction. In a chain reaction, newly emitted neutrons strike surrounding U-235 nuclei, triggering subsequent splits. Without intervention, this creates exponential branching. One split releases 3 neutrons, which then trigger 3 more reactions each. The result of this uncontrolled branching is rapid heat generation and a large explosive yield. A nuclear reactor aims for the opposite result, maintaining steady power by managing the heat over time. This is achieved through attenuation, the intentional absorption of excess neutrons before they can strike another nucleus. For the reaction to remain steady, engineers must intervene, removing 2 out of every 3 neutrons produced. This intervention turns an exponential cascade into a linear chain, where one split leads to exactly 1 more. The thermal energy from this linear sequence is used to boil water and drive turbines. The difference between a weapon and a power plant is determined by the mechanical mitigation of these neutrons. Nuclear fission is the opposite of fission, requiring the combination of light nuclei into a more stable state. The process typically uses 2 isotopes of hydrogen, deuterium and tritium. Because these nuclei are both positively charged, electrostatic repulsion prevents them from making contact under normal conditions. To breach this barrier, the nuclei need high kinetic energy, which requires environmental temperatures of approximately 10 million Kelvin. Once that threshold is met, the nuclei fuse. They produce a helium atom, a stray neutron, and a large outward pulse of energy. The resulting helium atom is stable and non-radioactive. Overcoming this electrostatic repulsion is the primary engineering challenge for fusion, but the energy reward per reaction is higher than fission. Comparing these reveals why fusion is the target for energy infrastructure. Fission operates at low temperatures, but produces radioactive byproducts like barium and krypton. Fusion requires a high temperature threshold, but yields stable, non-radioactive helium. Fusion also results in a significantly greater net energy yield. Currently, the global grid relies on fission because of its lower activation energy requirements. However, recent experiments have achieved 10 million Kelvin in laboratory settings, suggesting fusion-based power is physically possible on Earth. Understanding the mechanics of these reactions has allowed us to move from uncontrolled energy release to the threshold of harnessing the same mechanisms that power the sun.